Okay, today we're going to talk about gases in reactions. Because gases give us a little challenge with our technique. Okay? Our technique is we can't count moles, so we weigh stuff. Right? So, what's going to happen when you try to weigh a balloon full of hydrogen? Well, hydrogen is less dense than air. So you put the hydrogen balloon on the balance and it floats to the ceiling. It's going to be hard to figure out how many grams of hydrogen are in that balloon. Does that seem reasonable? I mean, because you could technically measure it, but what you have to do is get a balloon exactly the same size, figure out how much it would weigh with the air in it, okay? And see how hard the hydrogen is pushing up on the balance. You have to turn your balance upside down and see how hard it was pushing up, because it's pushing up as hard as how much lighter it is than the air would be. Because it weighs less than the air, that's why it floats up. Air's heavier, so it sinks underneath it, pushes it up. Okay. So we can't weigh gases. Okay. So what can we do? Well, the thing we could measure about gases is volume. Okay? And we're going to be able to change liters of gas to moles of gas. Now, we can't do it all the time until our next unit. We can do it for one set of conditions. It's called standard temperature and pressure, STP. So they had to pick one temperature and one pressure, because if I heat a gas, it gets bigger. If I squeeze a gas, it gets smaller. Right? So I want to compare all my gases at the same temperature and pressure. Okay? So the temperature they picked was the things where they picked were easy to recreate. So they picked 0 degrees Celsius and 1 atmosphere pressure. 1 atmosphere is a measure of pressure. It'd be 14.7 pounds per square inch, which is what your tires on your bike and car have. Pounds per square inch. How many pounds in each square inch of surface area? Okay, 0 degrees Celsius, they picked that because it's really easy to recreate. Because as long as you have melting ice in your water, that mixture should get to 0 degrees Celsius and stay there. So you can make it 0 degrees Celsius without a thermometer. Does that make sense? So, and at STP, 22.4, I know actually, because I need to put another sig fig there, 22.42 liters of gas make a mole. I don't want that to, we know the numbers. I don't want to limit our sig figs. So since the numbers get off the periodic table, usually have 4. I'll put 4 there, so that's 22.42 liters. So 11 2-liter bottles is 1 mole of gas, is 6.022 times 10 to the 23rd particles of gas, right? Because that's what a mole is. And if 6.45 grams of water are decomposed, how many liters of oxygen will be produced at STP? So that 22.42 liters is 1 mole. That's our conversion factor. So it's actually easier than what we did yesterday, because you don't have to figure out the number on top. It's going to, if it's liters, it's 22.4. 22.42. So first we write the equation for the decomposition of water. What's water going to fall apart into? Hydrogen and oxygen, right? So water falls apart into hydrogen and oxygen. And then we balance it by putting a couple of 2's in there. Because if I want to change which chemical I'm talking about, I need a balanced equation. And then we do the stoichiometry. So I get the 6.45 grams of water. What unit do I want to get rid of? Grams. Where's it got to go? The bottom. What can I turn grams of water into? Moles of water. So, and 2.02 for the hydrogen, 16.00 for the oxygen, adds up to 18.02 grams. And grams have canceled out on purpose. Now, what unit do I want to get rid of? Moles of H2O. Where's it got to go? On the bottom. What can I turn moles into? Well, the whole reason I turned it into moles was so I could change chemicals. So I don't want to talk about water anymore. I want to talk about oxygen. So I'm going to get rid of moles of oxygen, or moles of water, and get moles of oxygen. Have we done anything different since your homework last night? Okay. Here's the new part. They didn't ask me for grams of oxygen. They asked me for liters of oxygen. So I want to get rid of moles of O2. It's going to go on the bottom. And moles of O2 I can turn into liters of O2. 22.42 liters is 1 mole. If I'd asked you for grams, you would have had to add up O2. But it's actually easier than the homework last night. You don't have to figure it out. It's always the same number. And after all that, if you, with 3 sig figs, I got 4.01 liters of O2. So that gives us a sense of scale, okay? Because 4 liters, that's 2 2-liter bottles. So if I take apart 6 grams, that's the weight of 6 paper clips worth of water, I'll make 4 liters of oxygen. And look at my balanced equation, I'll make 8 liters of hydrogen. You say, why could you do that so fast? Well, every time I make 1 liter of oxygen, I make 2 liters of hydrogen, because I make twice as much, right? So I'd put 2 moles of H2 on top, and the next conversion factor would just be H2 instead of O2, right? So it'd make twice as much. So 6 paper clips gives you 12 liters of gas, 6 2-liter bottles full of gas. That's how much things expand when they go from liquid to gas. Because you know it's got to weigh less than 6.45 grams, because the oxygen is only part of water. Right? We can also change between particles and moles. That's the other thing we've done with this. And the particles and moles, the number was 6.022 times 10 to the 23rd. That was Avogadro's number. Or you could say there's Avocado's number in a guacamole. Avogadro's number in a mole, Avocado's number in a guacamole. Now, what are you counting if it's 6.022 times 10 to the 23rd? You're either counting molecules, if it's a molecular compound, atoms, if it's an element, and then the one that we always forget about, if it's an ionic compound, the smallest piece is a formula unit. And that's going to be our conversion factor. 1 mole is 6.022 times 10 to the 23rd something, right? And the formula will tell me whether it's an atom, a molecule, or formula unit. So yesterday, I showed you this little diagram. That you take the grams, change it to moles, change those moles into moles of something else. Then you change those moles back into grams of something else, right? This was our path yesterday. You did this all yesterday. And we got our numbers from the periodic table, the balanced equation, and the periodic table. Right? Well, today we've added that we can go from liters of something to moles. Or we can take those moles at the end and turn them back to liters. And the number there is going to be 22.42. The moles is going to be 1. And we can take particles, change it into moles. Or moles and change it into particles. And the number is going to be 6.022 times 10 to the 23rd. Right? So it's a map of all the possibilities. Okay, the one we did with grams of water to liters. We took the grams of water, used the number off the periodic table and changed it into moles. Then we used the number off the equation to talk about oxygen instead of water. And then we used 22.4 liters to figure out how many moles. So every step there is a conversion factor. See how we can put all those pieces together? So let's try some. How many liters of CO2 at STP will be produced from the complete combustion of C4H10? And I'll do the hard part. While you're copying, I'll balance the equation. 4 carbons, 4 CO2s, 10 hydrogens, 5 H2Os. That's 8 and 5, 13. Can't do 13. So give me 2 C2H4s, that gives me 8 CO2s, 10 H2Os, 18 and 10 is 8 and 10 is 18, so I can put a 9 in front of O2. Okay, now look at our pathway. They gave us grams, they want liters. So according to my chart, they gave us grams. They want liters of something else. So I'm going to take those grams, change it to moles, moles to moles, and I'll be able to go to liters. So 23.2 grams of C4H10. Rid of grams of C4H10, and that I can change into moles of C4H10. And 1 mole is 48.04 plus 10.1, so that's 58.14. You don't want to get rid of moles of C4H10. Change it into moles of a different chemical. They asked me about CO2. And in my balanced equation, the CO2 has an 8, and the C4H10 has a 2. And I want to get rid of moles of CO2. Change it to what they asked for, liters of CO2. 1 mole is 22.42 liters. So 23.2 divided by 58.14 times 8 divided by 2 times 22.42. Screen fills up with numbers. I get to write down 3 of them because the 23.2 has 3, 58.14 has 4, the 22.42 has 4. So this is going to be 35.8 liters of CO2. So the nastiest one. How many molecules of CO2 at STP are produced by completely burning 17.5 liters of CH4? And there's the balanced equation for the burning of methane. Well, we're going to start off with the 17.5 liters of CH4. The unit I want to get rid of is liters of CH4. Liters of CH4 I can turn into moles of CH4. 1 mole is 22.42 liters. So whatever they give me, I turn it into moles. Then I'll be able to change what chemical I talk about. So I change to moles, so I can change chemicals. I don't want to talk about CH4. I want to talk about CO2. In my balanced equation, those are both ones. There's a 1 in front of CH4. There's a 1 in front of CO2. Then I can turn my moles to CO2. What they asked me for? They asked me for molecules. So I'm going to change it to molecules. CO2, and 1 mole is 6.022 times 10 to the 23rd molecules. So my units work out. Got rid of liters, got rid of moles of CH4, got rid of moles of CO2, got just molecules left. So 17.5 divided by 22.42. I'm not pushing the ones, times 6.022 times 10 to the 23rd equals 4.70 times 10 to the 23rd molecules of CO2. Hugely different than what we've been doing before? No, we just get our numbers from a different place, right? Liters, we use 22.42. Pieces, we use Avogadro's number. So the way to get good at this is to practice, practice, practice. Do not try to do it in the space between the questions. If you want to use the bottom and the back, feel free, but you're gonna spend your time flipping. Does that make sense? You can write it on here, but you're gonna spend your time flipping. I might pick up a different one. There's only one side, and there's our map. That's how we're going to do it.